All right. Well, good afternoon, everyone. I'm Mike Fowler, and I'm here to talk about a technology coming out of the University of Guelph titled Electrochemical Remediation of Wastewater. So let me just get this going. So the major application that this technology is focused on is things like controlled environment farming. Two major concerns around the world are things like food security and sustainable water use, and controlled environment farming can address both of these issues. It can significantly reduce the amount of water consumed for agricultural purposes, for growing food. However, typically when that water is used, there will be wastewater produced, and that wastewater is not typically reused. One of the main concerns for the reuse of this kind of agricultural wastewater is pathogen spread. If you have a hydroponic or greenhouse that, a small portion of your plants become infected with some sort of pathogen, the last thing you want to do is recirculate that water full of pathogens back through the entire greenhouse and have your entire crop lost. There are methods available for decontaminating agricultural wastewater. However, conventionally they require either the addition of strong chemicals, or they can have extremely high power draws. For example, UV treatment, if in order to be effective, requires large amounts of UV light, which is consumes a large amount of power. And so this technology attempts to address all of these issues by using electrochemistry and some very specialized and unique electrochemical electrodes to generate the active chemicals that can decontaminate any pathogens from the water using background levels of materials that are already in the water, things like dissolved oxygen or trace amounts of chloride. And then once that decontamination has occurred, by the time that water recirculates back for agricultural use, that those chemicals have degraded back to their original forms and are no longer toxic or phytotoxic. And this allows full reuse, full recirculation of water, and that can significantly improve water use efficiency. So as the market advantage, the primary one this allows is that it enables full recirculation, full reuse of water in applications that it just hasn't been possible before, either because it's not a cost-effective way. I mean, certain pathogens can be highly resistant to certain treatment methods, or it's just not possible at all, that there aren't effective current ways to kill particular pathogens or to reduce any other materials that are in the water that you don't want to be there. And the way it does this is by in situ generation of the decontaminating agents. You're not consistently adding chemicals, building up salt concentrations in the water that will eventually kill the plants. You don't have to store, handle, or generate hazardous chemicals. So you don't have any of the regulatory or safety issues associated with chlorination or ozone generation. And overall, it can significantly reduce operating costs for any of these other alternative decontamination methods. The electrodes themselves are quite robust and long-lasting. They consume significantly less power than UV options, and you don't have to put anything else into the water that you otherwise have to pay for chemicals. And so overall, the operating cost reduction for this electrochemical technology compared to alternatives out there is significant, roughly half the power consumption of UV irradiation for decontamination. So overall, for market overview, specifically food-related water treatment rather than the overall water treatment picture, projected to be around $9 billion by 2025. And the controlled agriculture market in general is looking to be over $170 billion by 2025. Right now, the focus for the development of this technology has been greenhouses and controlled environment farming. So greenhouses are one of the first targeted markets. Even relatively small players, because the technology is scalable, you can run these electrochemical flow cells either side by side or in series or both if you need to increase capacity. So you don't need to make a massive investment for the product to start working, and that as the operation grows, you can easily scale the water treatment to the needs of the operation at present without having to completely restructure your water treatment system. And so greenhouses are the first target we're looking at, but the technology has applications outside of the greenhouses and controlled environment farming. I mean, industrial wastewater treatment, municipal drinking water treatment, these are all avenues that can be expanded into that may have more regulatory concerns, but greenhouses are what's currently being developed and tested for, with room to grow outside of that. So the core technology advantages that this provides, as I mentioned previously, because it's an electrochemical flow cell, you simply pump water that you'd be moving anyways, and it runs through the cell containing the electrodes. This really makes it easy to scale the technology, and it has no moving parts in and of itself, so it's a very robust and stable technology. Because of these specific electrodes, you don't have to add anything either, as a recurring chemical treatment agent or simply to enable the chemistry. I mean, it simply uses background materials that are going to be in the water no matter what. And currently, the various electrode materials are being evaluated to make sure that they have the kind of long-term performance that you need to make sure this will stand up to the day-to-day uses in real-world applications. And one of the biggest advantages, as I mentioned previously, is significantly lower power consumption, so that the cost of operating it long-term, both for keeping the electrodes maintained and for powering the electrodes, is significantly less than conventional alternatives like UV irradiation on the market. So right now, prototype units have been developed and they're currently being tested for long-term performance in hydroponic applications. Optimization and design changes to the flow cell itself are underway to improve the efficiency to ensure, both the highest efficiency generation of decontaminating agents possible, as well as maximizing output so that you can get the greatest amount of water purified per unit or per use of the electrodes. We currently have patent applications pending in the United States, in Canada, and in Europe. Right now, the team that we have here at Guelph consists of Thomas Graham, that's the principal investigator. There's a grad student, Serge Levesque, who's actively working on this project for his PhD. They've also employed the use of an on-site design engineer, so he's helping develop the actual prototype units to make sure that they have the best possible performance and that they can be used for long-term testing. And these people would all be available for scientific support, for consulting. But what we're really looking for right now is an entrepreneur who can pick this technology up and run with it to either build a company around it or add it to their existing tech portfolio. If anyone is in the water treatment space, if anyone knows of anyone in the water treatment space, I'd be happy to talk further and see if anyone can bring anybody into this that would be able to really move it with this technology. We would like somebody to just pick it up and run with it. So if there's any questions, I'm happy to answer them. Otherwise, my contact information is here. And yeah, so if there's any questions, please let me know.